Hello, this video describes the basic features of a theory of just about everything. I shall begin by describing the general sort of features and then to deal with each feature in more detail later. The first point is that the universe consists of abstract particles, not material ones. Material particles are defined as relationships between these abstract entities. Space-time only exists within the universe and does not exist outside of it. The universe began with a little whimper rather than with a big bang. The continuum does not exist, but is merely an approximation which is nevertheless exceptionally useful. The most relevant continuum which appears in this theory is that of a Grassmann space, which consists of Minkowski subspaces. Particles that appear in this theory are fairly closely related to the ones which occur in string theory, but supersymmetry is not involved. Gravity results from quantum theory and is distinct in nature from the gauge fields. Consciousness is vital to the material universe, and a limited degree of free will exists. I shall now describe these features in more detail, starting with the origin of the universe. The universe is created out of absolutely nothing. By that, I mean no matter, no light, no space, no time, and no information. The basic entities are completely abstract. The only intrinsic property which they have is their identity. And this property has to be exchanged. That is to prevent the existence of absolute information and also ensures complete fairness. The universe contains all possible numbers of identities, since to have only one specific number of identities would be absolute information. So the physical universe is then an interpretation of the mathematical universe of integers. The exchanges of the identities of the entities generate the symmetric group, otherwise known as the permutation group, so that the symmetric group on n identities is usually denoted Sn. The possible combinations of exchanges of identities can be classified according to the partitions of the number n into cycles of shorter lengths, so that the total sum of lengths of these cycles adds up to n. In a similar way, the entities can also be grouped into symmetry classes based on partitions of the number n, which are exactly equivalent to the division into cycles. These partitions consist of divisions into symmetric and antisymmetric subsets that are preserved by the exchanges. These are the bases of irreducible linear representations of the group Sn. The next topic to discuss is the nature of space-time. Sets of entities form the basis of space-time. Mathematically, a space is defined as an ordering between sets of entities. The most basic ordering of the universe is to put them into the ordering of the total number of entities, n. In this way, the successive function of arithmetic defines an evolutionary time for the universe. The next form of ordering is to divide the entities into subsets of equal numbers, call it R, of entities. This number is constant throughout the universe. Comparison with the physical universe suggests we should take the number 3 as the most likely form of R to be relevant. The identities of the basic entities define a coordinate system for the space, but due to the exchanges of identity, the coordinates can only be said to lie in the range 1 to n, where n is the total number of entities, rather than to have precise values. This vector space can be treated as continuous because it can be defined in a continuum of any dimension, although technically it's zero-dimensional because it's discrete. Together with the evolutionary time, these three coordinate vectors of one of the subsets define a four-dimensional space, which is a low-resolution limit to the discrete space. Each subset gives rise to its own four-dimensional space with a common evolutionary time. Together, these subspaces define a Grassmann space of the subspaces. Special relativity is known to be derivable from the projective geometry of a projective space 4 dimensions with a Lorentz type metric. So in that sense, we expect to find special relativity applicable in this theory of the universe. Furthermore, there is a finite maximum speed of light which comes into it, where velocity is defined as inhomogeneous coordinates of the projective space. And this finite limit arises from the fact there is a maximum ratio of distance to time corresponding to the maximum length n of a vector and a minimum length of 1. Any object moving through this space can be given its own real time. All these points are summarized in the following table. Once a space-time has been defined, it's possible to define material properties with the ideas of position and velocity already introduced as the bases. The feature which enables this is quantum theory. A local function on a group space can also be described non-locally as a reducible representation of the group, i.e. as a superposition of irreducible representations. Applying this to the position of an entity under the one-parameter subgroup of translations generated by a cycle of length n leads to an uncertainty relationship between position and the formal momentum defined as an eigenvalue of the translation group. This uncertainty principle is analogous to the Fourier transformation interpretation of the Heisenberg uncertainty principle in conventional physics. The Fourier transform is based on the special cases of harmonic analysis on the space of the one-dimensional abelian translation group and generalizes to harmonic analysis on other relevant non-abelian groups, including the symmetric group Sn and the Lorentz group. This implies that also an uncertainty relationship between precise geometric frame and irreducible Lorentz representations defined by the mass and angular momentum. Having introduced the idea of momentum, we can then move on to the idea of forces. Forces were introduced by Newton to explain acceleration and changes of momentum. In a geometric theory, such as this, acceleration is described by means of second-order G structures, where G is a subgroup of the second-order frame group. There are two non-trivial such structures, conformal and projective. Conformal structures and conformal theory in general have been very thoroughly studied, in particular the idea of twistors arising in the second-order conformal structure. Slightly less well known are the projective structures. Changes in the scale of each of the four dimensions are equivalent to accelerations, provided they are not all equal. Hence the invariance under conformal transformations and a conformal curvature tensor defining the gravitational field. The projective structure, which is also conformal, is invariant under a larger class of operations than the conformal, and these include the gauge transformations and inversions as it applies to scale-free rays as opposed to vectors. So this means that gauge fields, which can be derived from these extra transformations, in addition to the gravitational field which arises from the conformal structure. The projective structure was investigated early in the 20th century by Weil and Kaluza-Klein, amongst others, with somewhat limited success. But in this case, there's a much larger class to be investigated of transformations which are associated with the detailed structure of the Grassmann space. The first factor to consider in relation to this is how projective transformations apply to the symmetric group. This was investigated by Schur at the beginning of the last century through consideration of fractional linear transformations. He showed that essentially there were two different types of commutation relations and representations which apply to the symmetric group for projective as opposed to simply vector transformations. The first group, the ordinary vector representations, obey commutation relations, which one normally applies to the transposition operators of the symmetric group, which defines its exchanges, which are of the form 1 exchange with 2, 2 exchange with 3, 3 exchange with 4, etc., up to n-1 with n. These define n-1 independent parameters. In the case of projective representations, there are very similar types of relation, but they anti-commute as opposed to commute. This second set of representations, which applies as long as n is greater than 3, are the spinor representations. Whereas the vector representations of the symmetric group on n objects are in one-to-one correspondence with the ordinary partitions of n, the spinor representations are in one-to-one correspondence with the so-called strict partitions of n, wherein all the subsets of n are of unequal length. As a result of this, there can be no one-to-one correspondence between spinor and vector representations, and hence no supersymmetric theory is involved in this. Now I'm in position to talk about the properties of the particles as a whole. So if we consider a single subset of n, i.e. of 3 entities, each entity is associated with its own one cyclic spatial dimension and the evolutionary time. So the result of this is that the object as a whole has 4 spatial dimensions, 3 spatial and 1 common time dimension. But each entity can be associated with more than one subset, i.e. an entity called 1 can be a member of a subset with 1, 2 and 3 as members, but also with 4 and 5, or 6 and 7, or any other sort of set. So as a result of this, each entity appears to have a sort of 2-parameter internal space associated with it. So together, these provide an extra 6 dimensions. So this provides, in principle, an explanation of the 10-dimensional space which appears in string theory, in particular the type 2 symmetric string theories. The relationship of this model to string theory can be seen by considering the role of the single entity. A single entity is a point particle in the three-dimensional real space which we've introduced. That means that it is a Cartan isotropic vector because it has no length. Such a vector is a two-component spinor. But in addition to this, we've already mentioned the point that it's got an uncertain position, so it can be regarded as having a finite length as regards experimental details are concerned, and also it has an extended existence throughout time. So if you consider the two-dimensional approximate real space of the position of the entity in its one-dimensional space and the second dimension of time, then the second projective structure gives an equation called the conformal equation, which has a solution which is equivalent to a string. So that is the basic relationship of this model to string theory. Now, in relation to the model of the baryon, colour symmetry is associated with the extra two-dimensional spaces of possible positions for each entity, with the symmetric group acting on these. If you have a complex structure on each of the two-dimensional parameter spaces, and the symmetric group acting on those, then the complete group of operations on those are the SU3 colour operations. So that describes the origin of colour symmetry, but it doesn't explain isospin. The way this arises is from considering the energy momentum tensor. So far, we've talked about a formal momentum defined as an eigenvalue of one of the n cycles of permutations, and we haven't talked about time. So whereas the momentum is dual to these spatial translations defined by the n cycles, then the energy is dual to the cosmic time translations. And there's a slight difference here because the time translations are open-ended and time translations only generate a semigroup as opposed to a closed group of operations. And the consequence of this is that energy is not actually going to be conserved necessarily. And in fact, because the time translations of evolution generated by successor function of arithmetic also lead to the creation of new matter, then new matter and energy will both be created, which would be important on the cosmic time scale, and it leads to the modification requirement to general relativity to allow for this, which may provide an explanation for the so-called dark energy, which is used to explain the acceleration of the universe. So, when it comes to talking about energy momentum, it is still possible to introduce the usual four momentum of energy and three momentum components. But in the case of this theory, this is not nearly such a good symmetry as working with the energy momentum tensor, because the translations don't generate a global symmetry, whereas the energy momentum tensor can be combined with these permutations on a global basis to give a consistent global theory. And also the energy momentum, of course, tensor is much more convenient when working with general relativity in curved space. So, in order to discuss this further, we have to consider what the symmetry types are for the energy momentum tensor. The possible symmetry types of the energy momentum tensor in Minkowski's case were classified by Plebanski in terms of the numbers and types of eigenvalues and eigenvectors that they possess. There are four main types of these. The maximum symmetry, spatial symmetry of these is SO3. Together with the U1 symmetry operations, which are derived from the projective structure for spinors, this gives a maximal symmetry group of U2. This potentially provides an explanation for the isospin group. So a combination of this isospin group plus the colour symmetry operations gives the full symmetry group associated with the baryons. In the case of leptons, however, there is no symmetry group from the colour operations. So the only way to describe the leptons in this theory is to postulate that they apply to individual entities or possibly to pure energy. As regards string theory, the single and triple entities constitute open fermionic strings, whilst the exchange operators act as closed bosonic strings that carry the gauge fields and terminate on d-branes defined by the three-dimensional vector spaces. These bosonic strings, i.e. the photons and gluons, act within a single instant of the evolutionary time. Thus they would appear to move at the velocity of light and be massless entities. And in the time frame, measured along the real time of a material particle, the observer from such a particle would interpret objects in the distant areas of the universe as being in the distant past. The properties of the particles are summarized in the following table. That describes the basic theory of particles within the theory of the universe. The next topic to discuss is cosmology. In this, the theory differs radically from the Big Bang theory. The universe starts from a null origin, with matter and energy being progressively created due to the evolutionary time. To some extent, therefore, it would be more appropriate to say that the universe began with a little whimper rather than with a Big Bang. Time goes on forever after its initial start, and time is only defined within the universe, hence there is no meaning to the question of what happened before the origin of the universe. As time is open-ended and non-cycling, there is never any question of the universe either ending or collapsing in on itself and then re-expanding. This theory also avoids some of the problems known to exist within the Big Bang theory, at least in its basic forms. The basic form of Big Bang theory predicts equal quantities of matter and antimatter, which is contrary to observation. In this theory, antimatter only exists through short-term time reversals associated with the uncertainty principle. The next problem which the Big Bang theory has is in relation to homogeneity of the microwave background radiation. In this case, an overall homogeneity is guaranteed by the structure of the model universe. Then the next problem which potentially occurs in Big Bang theory is the explanation for the existence, the condensation of matter to form galaxies at the time which they are observed to start appearing. In this case, in the model universe, the nature of this condensation is really not required because the universe essentially grows from its null origin with basic sort of nuclei being formed in the earliest stages from the initial few particles. The next problem of Big Bang theory is in the expansion of the universe. This is driven entirely by the creation of new matter and new energy due to the evolutionary effects of time, as I already mentioned. This will require some slight modifications to general relativity. Obviously, in any other continuum theory, is not applicable in the very early stages of the universe anyway, and even in the Big Bang theory it's recognised as not being applicable right at the very outset of the universe. So in this case, the simplest modification to apply to general relativity, at least in the later stages when it is highly relevant, is to add an additional tensor field to describe the creation of matter. So this would be slightly analogous to the cosmological term lambda g mu nu. Instead of that, or in addition, we'd add a creation field c mu nu. A further fact is in relation to entropy. The universe automatically increases in entropy simply due to the increase in the quantity of matter and energy and in the number of states available. So more states, there is automatically more entropy. If one identifies the shortest distance in the model universe with the shortest distance postulated to exist in contemporary physics, i.e. the Planck length, and considers also the maximum length to be the radius of the observable universe, then this would give a value of approximately 10 to the power 61 or 62 for the value of n at the present time. So that summarises the cosmology in this theory. The final topic to discuss is consciousness. I mentioned at the outset that the universe only had some relative existence because there was no absolute information. So the question is, relative to what? And the answer to that is consciousness. So this requires the existence of conscious beings to arise naturally within this universe. So what is consciousness? From a mathematical point of view, at a very crude level, consciousness is the ability of a language to talk about itself and to have some model for this language which enables this. In the model universe, the basic way that an object interacts with its surroundings is through the existence of these exchange forces, gauge forces, which I've talked about already. So I have to have an organism which is sufficiently complicated to be able to interpret an action as something which affects itself. So this is a theoretical possibility in the sense that the mathematics does allow for this degree of complexity, but I certainly haven't shown that it's possible, let alone what types of consciousness could exist. But there is certainly the possibility. The information then of the universe is actually held in the collective consciousness of all the beings in the universe. This knowledge as general is going to be incomplete. And there is also the question of how everything is determined in the form of causality. Now, causality is effectively, in this universe, through logical induction, and in the absence of any information, this will mean that it's simply the most probable thing which will, on average, happen, and that's one of the fundamental laws. But at the outset of the universe, no information is set, so this is not a completely deterministic system, and the past is always contained completely in the present and the future. So logical induction gives a causality which essentially says that what was true before remains true in some sense because it's still submerged in the present and the future. But when it comes to the new matter which is being created, this is not being, its form is not determined by what has happened before. So in principle, a conscious being could try to act on the basis of something which they wanted to happen to be feasible, and some things which would involve the newly created matter could actually fall into place. So a certain degree of free will does exist, but it is very limited in the sense it would be competing consciousnesses of different beings coming into play, as well as the requirement of compatibility with the past. So this is a fairly intriguing possibility as to what really happens in the universe. So this is really the point I'd like to leave it. There is a technical question associated with that, which is that if you try to regard this system as a formal logical theory, because it is essentially mathematical in nature, then there is a question of what is the meta-theory. So the meta-theory is the proof theory of the universe, which is the laws of the physics and also all questions of any idea of justice. These are determined actually through consciousness, conscious observation in this model. And there is a slight drawback to this because it means the theory is subject to some of the mathematical logical laws which have been discovered. In particular, there's Gödel's laws of incompleteness, whereby if something contains complete arithmetic, including multiplication and predicate calculus, then the system is not completely decidable. It's either incomplete or it's inconsistent. So this is a limitation on the completeness of this theory which I'm discussing. So if anybody has any ideas on this, completely welcome to try to advance things further. This theory needs a great deal of work to be done on it to show that it really does explain physics, if it does. And alternatively, of course, it may be rather easy for people to debunk it. So, hope you've enjoyed it, and if you think it would be of interest to anybody else, please share it to them, because a lot of things on YouTube can't actually get noticed because there's so many competing videos on the same subject, and they just get buried unless they've got a very big ready audience. So, thank you for watching and listening.